not going to really introduce a whole lot of new stuff. Well, I mean, it depends on your perspective of new, but what we're essentially trying to recognize here is what our Lewis dot structures do for us after we have them. What do our Lewis dot structures do for us after we have them? So here are some examples of Lewis dot structures. Now, what we need to recognize is that when I have a Lewis dot structure like this one, CH4, methane, this carbon is bound to these 4 hydrogens. And it looks like, the way that I've drawn it, this would be a carbon with 4 90-degree angle bonded hydrogens to it, right? It looks like this is a hydrogen and this is a hydrogen, and that the angle here is 90 degrees, right? Well, we have to recognize that when we're dealing with 3 dimensions, it would actually look like this, right? The carbon with 4 hydrogens around it would actually find themselves at this angle, and that angle is 109.5. 109.5. So this angle here is not 90, it's 109.5 degrees, and that's not an intuitive angle. But the reason that occurs is because, like we saw, those atoms can use that third dimension, and spread out more, right? So they can spread out further from each other than just how we've drawn it on a plain piece of paper. Now, if we look at something like carbon dioxide, right? And the Lewis dot structure for that is, oops, what have I done? Okay, hold on a second. Lewis dot structure for that is like this, right? Carbon double bonded to an oxygen, like that, right? There's our Lewis dot structure. And we can see that those 2 regions of electron density, this is a double bond, but it's still just one region of electron density on top and one region of electron density on the bottom, result in a central atom with 2 binding atoms 180 degrees from each other. Okay? So our CH4 here, it has 109.5 degrees as the angle between the hydrogens. Carbon dioxide has 180. All right. If we look at something like, let me make another molecule here, boron here in the middle. Let me. If this is BH3 now, and if we did the Lewis dot structure for BH3, it would look like this, BH3. Now, we haven't talked a lot about that structure, and we don't have to worry about it too much. Boron is an exception. It can be in a stable situation when it only has 6 electrons available to it. But just for sakes of understanding the shape of the molecule, we bring that up as an example and recognize that the resulting angle then between the hydrogens in BH3 is, I don't know, what do you think, Alyssa? What's the angle between these hydrogens in this BH3? Any ideas?
Is it 109.5?
No, it's not 109.5. In this case, we have 3 things, and they're all in the same plane. Do you know, Alyssa? Go ahead.
What's 360 divided by 3?
That's right. 360 divided by 3, and that's 120. 120. All right. So, when there are only 3 binding or 3 regions of electron density, whether they're bonding regions or non-bonding regions, the result is 120 degrees, okay? So it depends, the angle depends on the number of bonding regions of electron density around the central atom. So, for example, if I have this compound here, NH3, now if we drew this out and took our time, we'd realize that we need 2 more electrons, a set of lone pair electrons. This compound here has 1, 2, 3 regions of electron density, and then there's the 4th region of electron density. So 4 regions of electron density, central atom, 1, 2, 3, 4 regions of electron density. Now, it might be hard for you to kind of see this, right? I'll draw this like it's getting bigger as it's coming towards you. And this one here like it's getting smaller as it goes away. But just like the CH4, the angles on these bonds is 109.5 because there's 4 regions of electron density. So this is 4 regions of electron density. Even though one of them is not bonding, still 4 regions of electron density. And because of that, I can know that the angle there is what, Anastasia? What's this angle here?
Is it 120?
No, it's not 120 because there's 1, 2, 3, 4 regions, right?
Oh,
So it's what?
right. 60?
Nope, when there's 4 regions, it makes this angle, which is 109.5, all right? Now, again, that's not an intuitive angle to us. Have you heard the joke about the football player who came to, or football coach who came to play football at university or college? I can't remember if it was a player or somebody, but they came and said, we're going to turn this team around 360 degrees, all right? Why is that a funny joke, Brielle? And if it's not, you just say, it's not a funny joke, Brother Scott. Camilla, do you want to help her out? It looks like her microphone's stuck.
Will you say the question again?
Yeah. Why is this a funny joke? That's the question. A football player comes to the team and say, we're going to turn this team around 360 degrees.
I'm not sure.
All right. Because if this is the direction the team's going, and now they're going to turn around 360 degrees.
180.
Yeah. The appropriate quote should be, we're going to turn this team around 180 degrees. So for all you exercise sports science majors, make sure you say it's 180 degrees. All right, because that's the 180 degrees. If you go 360, that's all the way around, right? So a circle is 360 degrees, okay? So because we know that a circle is 360, hopefully we have the ability to recognize if there's 3 regions, it's just 360 divided by 3, or 120, right? And if there's 2 regions, it would be 180, right? 180 degrees. So if there's 2 bonding regions. If there's 3 bonding regions, 120. If there's 4 bonding regions, we would be tempted to say, okay, 1, 2, 3, 4 bonding regions. And so we might say, oh, it's 90 degrees. But what's wrong with that, Camille? Why is that not true?
Well, if we're talking like the one below it, that's 109 degrees.
Yes, that's right. So why is it, what's the difference between this here and this here? Why wouldn't this 4 regions of electron density spread out to be 90 degrees apart?
Because can't the density be different?
Well, yeah, and why can't it spread out all the way to 109.5? What's going on there that it can get to 109.5?
Spherical?
What's that?
Is it because it's spherical?
Well, you could think of it that way. It's because we have 3 dimensions, right? So like this molecule here of CH3 or CH4, it has 4 regions of electron density, and they can spread out to 109.5 because it's not limited to, like our drawing is limited here, to a 2-dimensional surface. Okay?
Oh, okay.
All right, so we can have different shapes based on the regions of electron density. Based on that, here's a hard question for Chance. Based on that, here's our molecule of water. All right, our molecule of water, Chance. If we take this molecule of water and we want to tell somebody what the angle is between these 2 hydrogens, what would we tell them that angle is, Chance?
I would probably say 109.5.
Very good. Because there are how many regions of electron density around that oxygen?
4.
Yeah, 4 regions of electron density. 1, 2, 3, 4 regions of electron density around that oxygen there. Did anybody have any questions? All right.
I have.
Go ahead.
Um, can you explain that again? How do you know it's 109.5?
Well, the way we know the angle between the bonding regions is by counting the number of regions around the central atom. So we draw our Lewis dot structure, right? Now, this is one way to draw the Lewis dot structure of water, but some people might draw it like this. They might say, okay, I need these hydrogens to be as far away as possible, and now put those regions of lone pair density on there like that. And so somebody might say, oh, the angle here is 180 degrees. But just because I drew it away on the paper doesn't mean that that's what the angle actually is, right? What we do, Anastasia, is we count the regions of electron density around the central atom. And here we have 1 region, 2 regions, 3 regions, and 4 regions, right? There's 1 region, here's 2, here's 3, here's 4. So you count bonding regions, whether it's double or single bonds, as regions, and you count non-bonding regions as regions. And then we have to remember that if there's a central atom with 4 things bound to it, what's going to happen is one is going to be bound, one is going to be coming out toward us, one's going to be away from us, and then 2 will be in the plane. And now we just have to remember that 4 regions of electron density looks like this. And then we remember that the angle there is 109.5. And the shape here we call tetrahedral. Tetrahedral. Tetra meaning what? What does tetra mean, Chloe?
4?
Yeah, tetra means 4. So if this was a die and you were rolling it, or a shape, it would have 4 sides, right? 1 there, 1 here on the left, and then 1 on the back, and then 1 on the bottom. So this would be a 4-sided figure. Does that make sense, Anastasia, how we knew that the angle here was 109.5?
Yes, so every time there's 4 pointing, then the angle will always be 109.5.
For now, that's right. That's right. 4 regions. So
okay.
the angle is dictated by the regions of electron density.
Okay.
Very good.
Thank you.
Yeah. So then, counting the number of regions of electron density becomes critical for us. I think that we could do all of these. I think we have actually done all these 3. But here's one on the top right. Emily Eddington, can you tell me how many regions of electron density are around the central atom here?
Are there 3?
No, we have 1 region here, 2 regions there, 3 there, but then we have to count these ones as well, 4 and then 5. So that's 5 regions of electron density around that central atom. Can you see that, Emily?
Yeah.
All
I
right,
can see
great.
it now.
So then the question is, what happens when we have a compound with 5 regions of electron density? Okay, so let's bring up our little thing here. We're going to make this a phosphorus and make 1, 2, 3, 4, 5 things coming off of it. We're going to clean it up a little bit, and then we're going to show what it looks like in 3 dimensions. So this is what happens. All right, when you have 5 regions of electron density bound to a central atom, you get this. It kind of looks like a jack. Do you guys remember what jacks are as kids? Almost like a jack, but not quite perfectly.
Yeah.
So what we have is we have 2 regions of electron density in what we call axial locations, up and down, 180 degrees apart, and the remaining 3 are in what we call equatorial regions. So if we visualize this as the Earth spinning on its axis like this, right, then these 3 are in equatorial regions and 2 are in axial positions, okay? Now, these are slightly different positions. So you can see that if we look at this element right here, maybe we'll just look at this one right here, and we look at its neighbors. It has 2 neighbors that are how far apart, Ephraim? How far away is this element, this chlorine, from that chlorine right there? Can you tell? Ephraim, can you write it down below? Joey, any ideas? How far is this from there?
120 degrees.
120 degrees. That's right. There's 3 of them on this circle here, and they're all 120 degrees from each other. So this chlorine is 120 degrees from that one and 120 degrees from that one. However, Joey, how far is it from its axial neighbors, up and down? How far away is that from its axial neighbors?
Maybe 90.
That's right. It's 90 degrees from its axial neighbors. So when you have 5 regions of electron density, what that means is 3 are axial, so axial, and 2 are equatorial. No, other way around. 2 are axial on the axes, and 3 are equatorial. So 3 are equatorial and 2 are axial. So this is what we have to visualize. We call this shape a trigonal pyramid. Can you see how these 3 on the equator make a triangle, with this being a pyramid's point, right? So it's a trigonal pyramid. But we also, it's not just one pyramid, is it? There's another one on the bottom, another pyramid on the bottom. So this is called trigonal bipyramidal. Trigonal bipyramidal. So the shape is basically called what it is. It's 2 pyramids upside, or one on top of the other. So we call it trigonal bipyramidal. Okay? All right. If I take a, let's see, there we go. If I take a central atom and add 6 ligands to it, whoops, that is not a very good structure. That didn't work out the way I wanted to. Let me draw this one. If I take a central atom and add 6 ligands to it, then you can imagine one being up and one being down on the y-axis, one being right and one being left on the x-axis, and then a z-axis coming out toward us and then going way back into the plane. All right? And the result of this shape here, you could think of it as square bipyramidal, but we have a special name for this called octahedral. Octahedral means 8, and what it's referring to is the 8 sides that this shape would have if it were like a die. Okay? So what we're learning is that we can identify the shape of the molecule based on the regions of electron density that are around the central atom. Okay? And this method of identifying the shape of the molecule based on the regions of electron density around the central atom is called VSEPR, or valence shell electron pair repulsion theory. Now, you don't have to remember this too much, but if we look closely at what this slide is showing us, it's showing us that sometimes you have 2 regions, that would be a linear relationship, 3 regions. This one we call planar, but it's because it's all in one plane, but it's triangular, so we call it triangular planar or trigonal planar. This one, does anybody remember? Let's see, whose turn is it? Catherine, do you remember what we called this one here, where there's 4 regions of electron density around a central atom?
I don't remember what the 4 one is, no.
Okay, the 4 one has to do with the prefix for 4. Do you remember what the prefix is for 4?
Oh, Trent. It was like Trent.
Do you remember the game? Did you ever play that game where there's shapes that have 4 different blocks in them coming down in different organizations, and you have to get 4 things to disappear, 4 lines to disappear?
I don't think so. I don't think I played that game.
It was one of your homework assignments to go home and play Tetris, remember? Long time ago.
Tetris.
Yeah, Tetris. So this is a tetrahedral. Tetris is all about 4. All the shapes that come down have little segments of 4 blocks, and they're all organized in different ways. So this is called tetrahedral. All right, let's see. Kylie, do you know the name of this molecule? 5 regions of electron density.
I don't, but I know the prefix is penta, so.
We just talked about how this shape here is like 2 pyramids that have triangular bases. Does that help you? Rebecca, do you remember what the name of this is?
Is it for 5?
For 5, yeah, this one right here. What's the name of this shape right here? It had to do with the fact that it's like 2 triangular pyramids.
I can literally picture your drawing of it. Hold on.
It's called trigonal bipyramidal. Trigonal bipyramidal. Right? Because it has trigonal, 2 triangular pyramids. So it's trigonal bipyramidal. Okay. Ryohi, can you tell me what the name of this last shape is here? We just talked about it. Sarah, what's the name of this shape?
Octahedral.
Very good. Octahedral. Excellent. Okay. Oh, Ryohi, there you are. So, see this shape right here, Ryohi? This one right here that I'm circling? Can you tell me the angle between these 2 bonds, this MX bond here and this MX bond here? Can you tell me that angle between those 2 bonds?
120.
No, it's not 120.
109.5.
109.5, that's right. We know that. How do we know that, Ryohi?
I don't know. It's just same as the top one.
Okay, that's right. Because there's 4 regions of electron density. There's one up here. This one in this case is non-bonding, but it's still a region of electron density, and then 3 down on the bottom. So the 4 regions tell us that the angle between the regions is 109.5. Okay, Zaf, what's the angle between this MX bond here and that MX bond right there? You can type it down below. No, it's not 90 degrees. The angle isn't dependent on what we think it looks like. The angle is dependent on the regions of electron density. Zaf, how many regions of electron density are attached to this central atom here, this M? How many regions of electron density are attached? No, not 3. There's 2 bonding. The X's are bonding regions, and then there's 1 non-bonding region here and 1 non-bonding region there. So a total of 4 regions. And whenever there's 4 regions, then they spread themselves out in such a way that the angle between them will be 109.5. Okay. Very good. Alyssa, this is a little bit of a hard one here, but we have this shape. Let's start with this shape here. All right. Can you remember the name of this shape, Alyssa?
Which one's the one around the equatorial, or?
Just the name of the whole shape.
Oh, the trigonal bipyramidal.
Very good. Trigonal bipyramidal. And then if we look down here, can we predict, or can you tell me what the angle is between the equatorial X here and this equatorial X here? What's the angle there between those 2?
120.
120, that's right. Those 3 equatorial regions spread out. Notice that when you put a lone pair, right, this is the lone pair, lone pair, these regions are lone pairs. When you put a lone pair region of electron density in a tetrahedral, it doesn't matter which one you put it in, it will result in the same structure. If you put it in a lone pair in a trigonal planar, it's same thing. It won't matter where you put it. The resulting angles will all be the same. Same thing with an octahedral. If I put the lone pair here on the bottom, or if I put it on the side, it would end up with the same shape. It wouldn't be drawn the same here on our paper, but if I were to rotate the structure, I would see that it was the same shape. However, this is the only shape that trigonal bipyramidal is the only shape that when you put lone pair density on, the lone pair density always goes to the equatorial space. And that's because the lone pair takes up a little more space. Now, why do lone pair electrons take up a little more space? And there is more space available to them in the equatorial region. Now, why do lone pairs take up more space? Well, you can think of it like this. If there's two nuclei and there's electron density between them, the electron density will take up some space, but because there's a nuclei at the other end, the electron density will be kind of shaped down a little bit. But if this is a region of lone pair electron density, there's nothing on the other side to kind of draw that electron density back in, so it ends up being a little bit larger and taking up more space. Okay? So, for a trigonal bipyramidal, those lone pair electrons always want to go into what location, Anastasia? What location do the trigonal bipyramidal lone pair electrons want to go, Anastasia, in a trigonal bipyramidal? Camilla, are you there? Where do the lone pair electrons want to go when we're talking about putting them into a trigonal bipyramidal molecule? Camilla?
Where do the lone electrons want to go?
Yeah. What if the lone pair electrons are going to replace atoms in this trigonal bipyramidal molecule? Do they want to go in the equatorial locations? Sorry, the axial locations or into the equatorial locations?
I'm gonna guess the axial, but I'm not positive.
Okay. Well, can you see here when lone pair electrons are replacing these atoms, are they going in the axial, or what do we call, I mean, which locations are they filling here?
Equatorial.
Equatorial. Very good. They like to go in the equatorial region. Camille, can you think of any reason why they prefer to go to the equatorial region?
I don't know. Is there more space?
That's right. There's more space. There's more space. That's the answer. Okay. Very good. So these next slides tell us our names of our shapes. Call this linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. All right. This slide here talks about our lone pair taking up more space. All right. So then what we want to do is be able to answer questions like this. Here's a molecule. What is its geometry? What's the geometry of this molecule, SO2? Okay. Now, we have a couple of ways to think about this. We either have what's called the electron domain geometry, or we have just the molecular geometry. Now, first we have to draw SO2. Okay, here we go. Where are we at? Chance, you're going to help me draw SO2, okay? Central atom. What's the central atom?
S.
S. So I'm going to put the oxygens on the outside like that, right? How many electrons in this party?
In the total party.
Uh-huh.
So you got 6 for the sulfur and then 6 for each oxygen.
Right. So 18 electrons, right?
Yep.
18. Whoops. What have I done there? Okay, 18 electrons. Okay.
Yep.
4 electrons already up there, right? So I have 14 electrons left to go. 14 electrons. Where am I going to put them first?
Put the remaining ones on the S.
Okay.
Right?
So it looks like it needs 4 more. Is that okay? Now I need 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What can I do to fix my structure now, Chance?
Create a bond.
Between where?
The sulfur and the oxygen on the left.
Okay, so we're going to do that sort of thing. So we have S with a double bonded oxygen like that, and now we have oxygen like this. All right, are we done?
No,
How can we tell?
because sulfur is, it looks like it's only bringing 5 right now.
All right, so its formal charge is what right now?
It's positive 1.
Yeah, formal charge here of positive 1, and the formal charge of oxygen?
Negative 1.
Negative 1. Very good. Okay, so how are we going to fix that?
Create another bond between the sulfur and the oxygen.
All right, like that?
Yep.
1, 2, 3, 4, double bond there, double bond here. Whoops, that wasn't a very good placement. All right, so now we have a molecule where there are 8 electrons available to everybody. In fact, sulfur has more than that, right? Is that okay to have more electrons available to sulfur? Chance?
Yeah,
Why? How do we know?
because it is
Third row or lower, right?
yeah, that's right. Yeah.
On the periodic table, meaning it can have an expanded octet. Okay,
That's right.
and no formal charges on any of these molecules. Now, what do you think is the angle here between these, Chance?
Between those two,
Yes, between those two oxygens.
I'll probably say 120.
120, and that's right, because we have 1, 2, 3 regions of electron density. Now, you know in the test, they're going to draw it like this. They're going to draw S, O, O, right? To try to make you look like it's 180 degrees between the bond angle between those two oxygen bonds are 180 degrees, right? But it's not what it looks like how you've drawn it. It's the number of regions of electron density that decides that angle. Okay, very good. Now, in terms of the shape of the regions of electron density, what do we call central atom with 3 regions of electron density? What do we call an atom with 3 regions of electron density? Chloe's turn. Central atom, 3 regions. What would that shape be called?
Trigonal planar.
Trigonal planar. That's right. It's all in the same plane, forms a little triangle. Now, what do we call, and we didn't really talk about this, but it might be a little, it might be more intuitive than we think. This is for you, Emily. What do we call a shape where, of the shape of the molecule, if 2 regions are bonding and 1 region is just a non-bonding? The resulting shape of the molecule is different than the shape of the electron density, right? So this one is trigonal planar. Emily, do you have any idea what we would call that one?
Would it be bent?
Bent, that's right, bent. And Emily, what's the angle here, did we say?
120.
120, very good. Excellent. So when they say, what is the geometry of SO2, they're asking about the molecular geometry here, which is bent, whereas this, the electron domain geometry, is trigonal planar. So this question should have been cleaned up a little bit. It should have said clearly what's the molecular geometry, so the shape of the resulting molecule. All right, very good. So then, it's the number of regions of electron density around the central atom and whether those regions are bonding or non-bonding that tells us the molecular geometry of these structures. All right, Ephraim, you can type in the question down below. What is the shape of this molecule right here? CH4, what's the shape, the molecular shape, or the molecular geometry or shape of this molecule, Ephraim? So what we do is we count the regions of electron density. How many regions of electron density are there, Ephraim, around the central atom? 4, that's right. 1, 2, 3, 4, no non-bonding electrons. So if there's a central atom with 4 regions of electron density, what do we call that shape, Ephraim? Okay, Joey, any ideas?
Tetrahedral.
Tetrahedral. Very good. So the shape of the molecule is tetrahedral. Now, this happens to be the same shape, or the same shape of the electron domain regions. It's also tetrahedral because none of them are non-bonding. Now, this molecule here, Joey, just looking at the domains of electron density, what's the shape of the electron domains for this molecule, Joey?
Well, there are still 4 regions, so it's still tetrahedral.
That's right, it's still tetrahedral. But the shape of the molecule, Joey, what do you think is the shape of the molecule? So we have 4 regions, right? We have 4 regions, one coming out toward us, one going away from us in the back, and then 2 in the plane, right? And what are the angles here, Joey? 4 regions of electron density, what's those angles?
109.5.
109.5, right? But 2 of these regions now are going to be occupied by lone pair electron density. So the resulting shape of the molecule, what does it look like, Joey? Emily, are you there? Want to help him out? What is the shape of this molecule here? Emily, are you there? This is also bent. Central atom, 2 ligands, and they're at an angle, right? It's bent. It's not 120 degrees like this bent one was here. This is bent at 120 degrees, but this is bent at 109.5 degrees. Does that make sense, Joey?
Yeah, it does.
Okay. Kylie, what's the shape of this molecule right here?
I'm not sure.
Okay, how many regions of electron density around the central atom? 2. 2 regions of electron density around the central atom. That's it, that's all. So here's a central atom. Those 2 regions are going to try to get as far away as possible. So the resulting shape would be called linear. Does that make sense?
Yeah.
Okay, very good. Rebecca, the shape of the electron domains of this molecule, the shape of the electron domains here is tetrahedral. However, when one region is non-bonding, right, Rebecca? When one region is non-bonding, the resulting shape looks like this. So I'm going to draw our, start over. I'm going to draw our tetrahedral shape. Where this one's kind of coming out at us a little bit. This one's going away in the back. And these 2 are in the plane of the paper. All right. And now I'm going to take these and make this one a lone pair section, right? A lone pair region of electron density. The result is these 3 regions of electron density. Can you predict in your mind what that shape might be, Rebecca?
Maybe bent again? I don't know.
Let me get here, erasers here. Okay, there it is, Rebecca. It's not quite in the plane. Can you see that, Rebecca?
Uh-huh.
And so what we call this is trigonal pyramid. It's a trigonal pyramid. It's kind of a shallow pyramid, but can you see how it's a trigonal pyramid?
Yes.
Okay.
Kind of.
This might help a little bit. Okay. So
Okay, that more.
yeah. So what we have here is how many regions of electron density? Now it's tricky when I have the molecule up here, or sorry, in this software. How many regions of electron density are there?
3?
Well, there's
4.
There's 4. There's 3 bonding regions, but this fourth one, which is a non-bonding region, we can't see because there's no atoms there, right? But that's why these 3 are bending down away from that atom there.
Okay.
Okay, very good. So,
I have a question.
yeah.
So why did we say the CO2
Yeah.
was linear, but then we said that SO2 was bent?
Okay. So we bring back our paper here to see, to see what SO2 looks like, right? SO2 look like that.
Mm-hmm.
Can you think of a reason why SO2 was not linear?
Is it because the S has more electrons?
Yeah, there's 3 regions of electron density. One here, one here, and one there.
Okay.
So I've drawn it like that, but in reality, it's a region of electron density, and these 2 are trying to get away like that.
Okay.
Okay, very good. Whoops. So what am I looking for here? Where's my... Okay. Now, one more thing. It turns out that the angle between the hydrogens on water is a little less than 109.5. And now I just told you it was 109.5, so, you know, you would say, oh, man, we're lost, we're gone. It's not true. It's very close to 109.5, and what we say is it's a little less than 109.5. And the reason it's a little less than 109.5 is because these 2 lone pairs, what did we say about lone pairs as opposed to bonding pairs? Raihohi? If we have lone pairs, what did we say compared to bonding pairs? How are they slightly different in the amount of space they take up?
There's more space, I guess.
That's right. The lone pairs take up more space, and so it results in these hydrogens pinching together slightly. So what we say is it's a little less than 109.5. All right. We just talked about that. Okay. So, resulting molecules that are asymmetric in their shape can be then called polar molecules. Now, we've talked about polar bonds being asymmetric in the amount of electron density that they want to stabilize, right? And that's based on electronegativity. And molecules can also become or be identified as polar based on their resulting shape or their resulting, which is related to their resulting electronegativity to a degree. So water, for example, right? It's bent with the angle a little less than 109.5 here. And we have these regions of electron density up here, regions of less electron density down here, because this oxygen-hydrogen bond is polar already. All right, Zaf, or let's see, no, Sarah, do you know where our electron density wants to reside on that oxygen-hydrogen bond? Sarah?
Does it want to go near the oxygen?
That's right. And so we say this is a partial negative charge, and here's a partial positive charge, right? The same thing is happening over here on this side. So the result is we have water, and water is, because of this polar bond and because it's misshapen, it's asymmetrically shaped, we have a polar compound. A polar compound. Okay? Now, carbon dioxide. Carbon dioxide, is the carbon-oxygen bond polar, Zaf? Do you think the carbon-oxygen bond is polar? Yes or no down below. Is the carbon-oxygen bond a polar bond? Alyssa, what do you think? Is the carbon-oxygen bond a polar bond?
No, I don't think it is.
Well, it actually is. It is a polar bond. Now, how did we know that? How are we supposed to know that? That was the previous chapter, knowing the electronegativity, right? Carbon is going to be polar with anything that's nitrogen, oxygen, and fluorine. In fact, any bond that contains nitrogen, oxygen, and fluorine is going to be a polar bond because those are the big hogs, the electron hogs, all right? If it's nitrogen and oxygen, the electron density is going to be leaning towards oxygen. If it's nitrogen and fluorine, towards fluorine. Oxygen and fluorine, towards fluorine, right? So carbon and oxygen is a polar bond. What do you think, Alyssa? Where's the electron density going to be leaning in that carbon-oxygen bond?
It should be leaning towards the oxygen since it's more electronegative, right?
That's right. That's right. And so we have a slight difference in electron density on this compound. Now, although these bonds are polar bonds, because the resulting shape of the compound is symmetrical, it results in a compound that is still non-polar. All right? So it's not enough to have electron density moving some direction, because if the shape of the molecule is symmetrical, then the net movement of electrons is not going to be evident in the compound. And so the compound is going to be non-polar. So for a polar compound to exist, we need to have polar bonds and an asymmetric molecule. Okay? So here is an example of a compound CF4. CF4. All right. Who do we got? Anastasia. CF4. Is this compound going to be polar or non-polar?
Polar.
Okay. What made you think it was polar?
Because carbon.
Yeah, look at that choice. I should have left like that.
Okay, because carbon what? Well, if we look at this compound, if we draw it out, CF, F, 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 right? 4 regions of electron density. The carbon-fluorine bond is surely polar. However, the symmetry in this molecule results in a compound that is not polar. So this is a non-polar compound. Okay? Does that make sense, Anastasia? The carbon-fluorine bond is a polar bond. However, because its shape is symmetrical, the result is a non-polar compound.
Oh, okay.
All right. Camille, you ready for a question?
Yes.
All right, here it is. NCl3. Is NCl3 a polar or non-polar compound?
I feel like it's non-polar.
Okay. What we need to do, though, is what do we need to do to know? What are the 2 things we need to know, to know? How can we tell whether it's polar or not? What are the 2 ways? It needs to have a polar bond in there somewhere, right?
And then I'm assuming it has to look like one of the mulch.
It needs to be asymmetrically shaped. So we have to draw the Lewis dot structure. And the Lewis dot structure, if we were to draw it, take our time and do it, we would see that it looks like that.
So would that be polar?
It would be polar.
Yeah.
Because what's the angle between those two chlorines there?
109.5.
That's right, 109.5. 4 regions of electron density. What's the shape of this compound? You know the name of that shape?
Try something.
Triangular. That's fine. That's close enough. Triangular what?
It starts with a P.
Pyramid. It's a triangular pyramid or trigonal pyramidal.
Oh, yeah. Okay.
Okay. Very good. So what we have here is tools to identify the shape of the compound based on, and we know the names of those shapes, and we also can identify whether or not the compound is polar. Because to be polar, you need to have some polar bond where electron density is moving somewhere, but then you also need to have a non-symmetrical, asymmetrical shape of your compound. All right, very good. So we learned a lot of stuff today. Let's see what we could not learn because we ran out of time. Not bad. Very good. So the final, like I said before, will probably